Okay, let's unpack this. Have you ever stood before a towering mountain range or admired a stunning marble statue and wondered about the immense, unseen forces that must have shaped them? Today, we're taking a deep dive into Earth's hidden world, exploring how rocks transform under unimaginable pressure and heat, telling a dramatic, millennia-long story of our planet's dynamic past.
It's truly fascinating, isn't it?
Yeah.
We often perceive rocks as static, unchanging things, but they are constantly being remade.
Constantly changing.
This deep dive into metamorphism is like getting an exclusive backstage pass to Earth's most powerful rock-making processes far beneath the surface, giving us crucial insights into the very mechanics of our planet's crust.
Absolutely. Our mission today is to explore Chapter 8 from Earth, an introduction to physical geology by Tarbuck, Lutchins, and Tessa. We're going to uncover the central theme of metamorphism, literally the changing form of rocks,
The change form, exactly.
and guide you through the major concepts, the incredible agents, the unique textures, and the environments that forge these incredible metamorphic rocks. Get ready for some genuine aha moments because we're going to help you visualize Earth's structures and processes without a single visual aid.
Yeah, that's the challenge, painting that picture.
So, unlike the fiery birth of igneous rocks from molten magma or the patient layering of sedimentary rocks on the surface, metamorphism operates in a different, often invisible realm deep within the Earth. But how exactly does this change form happen?
That's the core question, right?
Yeah.
And geologists act like forensic scientists, using clever techniques to decipher the extreme conditions a rock faced. At its heart, metamorphism is the transformation of one rock type into another,
Okay.
meaning every metamorphic rock has a parent rock, the original material it came from.
The starting point.
Exactly. This process fundamentally alters its mineralogy, which is, the specific mineral ingredients present, and its texture, how those individual grains are arranged. Sometimes, even the overall chemical recipe can shift.
So, the parent rock is like the original genetic code. It determines the starting point, but then Earth's forces completely rewrite its story.
That's a great analogy.
To give you a tangible example from our sources, think of simple clay minerals, incredibly common in sedimentary rocks and stable at the surface. But if you bury those clays to about 8 kilometers, or 5 miles deep, where temperatures hit around 200 degrees CO, that's nearly 400 degrees F, they completely transform. They become new, more stable minerals like chlorite or muscovite mica.
Right, they can't handle the heat and pressure as clays.
And if conditions get even more extreme, that chlorite can then change into biotite mica. It's a progression.
That progression beautifully illustrates metamorphic grade, which describes the intensity of these changes. At low-grade metamorphism, with lower temperatures and pressures, the transformations can be quite subtle.
Okay.
Imagine a soft shale, a common sedimentary rock, simply becoming a more compact slate. By hand, these can sometimes be difficult to distinguish, showing a gradual transition.
So you might not immediately see a huge difference.
Not always. But at high grade, with extreme temperatures and pressures, the transformation is complete. Original features like bedding planes, ancient fossils, or even gas bottles are totally obliterated.
Wiped clean.
Yeah. You might even see rocks fold intricately, like a plastic sheet, due to intense compressional stress, transforming a rock like granodiorite into a beautifully folded gneiss.
So if it's changing form so dramatically, does the rock ever actually melt, or does it stay solid throughout this transformation? That's always been a point of confusion for me.
That's a crucial distinction, and the answer is it always occurs in the solid state.
Always solid, okay.
If a rock completely melts, we're talking about igneous activity, a different geological process.
We know.
Metamorphism has a fascinating sweet spot for temperature, typically occurring between 200 degrees C, where sedimentary rocks form, and about 700 degrees C,
Right.
which is where rocks start to melt but haven't fully done so yet. It's like extreme baking, not melting.
Here's where it gets really interesting. What actually provides the energy and the force for these incredible transformations? What are Earth's geological sculptors using to carve and reshape these rocks from within?
Well, there are four key drivers, or agents, of metamorphism: heat, pressure, directional stress, and chemically active fluids.
4 main things.
They often act simultaneously, but their influence varies greatly depending on the specific environment. Let's start with what many consider the most important one: heat.
Heat. Okay, so heat is the primary engine, literally cooking the rocks into new forms.
Pretty much. It provides the energy for those crucial chemical reactions and for recrystallization,
Recrystallization, right.
which is where existing mineral grains rearrange and often grow into new, larger forms. The original minerals might not always change, but their atoms certainly rearrange into more stable structures.
And where does this intense heat come from deep down?
Two main sources. One is the geothermal gradient, the natural increase in temperature with depth, averaging about 25 degrees C or 77 degrees ARS per kilometer in the upper crust.
So just going deeper makes it hotter.
Exactly. The deeper you go, the hotter it gets. The second major source is heat released from cooling magma intrusions that essentially bake the surrounding host rock like a geological oven.
Ah, okay, like a magma chamber nearby.
Precisely. You see heat-driven metamorphism in active areas like convergent plate boundaries, where oceanic slabs subduct, deep sedimentary basins like the Gulf of Mexico, during continental collisions that build massive mountain ranges, or near-rising mantle plumes in mid-ocean ridges. Lots of places.
Now, it's not just about the temperature, is it? We often talk about immense forces shaping mountains, and that implies another critical agent. So what about pressure?
Absolutely. That brings us directly to pressure, and it's a bit more nuanced than you might think, because there are actually two types at play. First, confining pressure.
Confining pressure.
Imagine the immense pressure you'd experience at the bottom of the ocean. It's applied equally in all directions.
Like being squeezed evenly from all sides.
Exactly. This type of pressure increases with depth, forcing mineral grains closer together, making rocks denser. It can even cause phase changes, where one mineral transforms into a new, denser mineral with the exact same chemical composition. But importantly, confining pressure doesn't crumple or fracture rocks.
Okay, so it compacts things but doesn't fold them. That's where the forces we associate with mountain building come in, right? The kind of pressure that literally squeezes the earth.
Exactly. That's differential stress. This is when forces are unequal in different directions, a common occurrence at convergent plate boundaries where massive slabs of lithosphere collide.
Unequal forces. Got it.
If that differential stress is compressional stress, it squeezes a rock mass like it's in a giant vise, shortening it in the direction of the greatest stress and elongating it perpendicular to that stress.
Like squeezing dough.
Yeah, that's a good way to think about it. This is absolutely key in mountain building, causing the crust to dramatically thicken and fold.
And the impact on the rocks themselves is incredible. In high temperature, high pressure, ductile environments where rocks can flow rather than break.
Yeah, where they behave like putty almost.
Mineral grains actually flatten. Our sources describe it like stepping on a tennis ball that flattens out, or a thick paste developing intricate, wavy folds.
It's a good visual. But near the surface where temperatures and pressures are lower, rocks are brittle and tend to simply fracture and pulverize under differential stress instead of flowing.
So they shatter instead of bend.
Right. The third agent is chemically active fluids. Water is incredibly abundant in Earth's crust and at depth becomes hot and rich in dissolved ions.
Hot, soupy water.
Pretty much. This fluid plays a crucial role by dissolving and transporting ions, which greatly enhances recrystallization. These fluids come from various sources: groundwater percolating down, water expelled from cooling magma bodies, or even water released from hydrated minerals like clays as they dehydrate at higher temperatures and pressures.
And sometimes these fluids do more than just help things along. They can actually change the rock's recipe.
Yes, exactly. If they transport mineral matter over considerable distances, bringing in new atoms or taking out old ones, the overall chemical composition of the rock actually changes. This process is called metamorphism.
Metamorphism. Okay, so a fundamental change.
It's a fundamental change to the rock's identity. Think of it like this. If silica-rich fluids invade limestone, the calcite in the limestone can react with the silica to form a new mineral called wollastonite. It's not just reorganizing what's there, it's introducing new ingredients.
Wow, so the fluids are like couriers bringing new elements.
In a way, yes. Ultimately, the parent rock's initial chemical makeup is the most important clue to its metamorphic history. The original minerals determine how it will react to these metamorphic agents, guiding its unique transformation path.
Okay, so parent rock chemistry is key. Now, beyond just changing minerals, metamorphism literally reshapes the rock's look and feel. So when geologists look at a metamorphic rock, how do they describe what they see, even without visuals? How does a rock actually show the stress it's been under?
This brings us to texture, which describes the size, shape, and arrangement of mineral grains within a rock. What's particularly characteristic of many metamorphic rocks, especially those formed under intense pressure, is foliation,
Foliation.
a distinctive planar or nearly flat arrangement of minerals. It's like seeing a preferred direction or layering in how the minerals are lined up.
Like lines or sheets within the rock. And foliation is a fundamental characteristic of strongly deformed metamorphic rocks, typically driven by that intense compressional stress. So how does that actually develop?
Well, there are a few ways. Existing platy or elongated minerals like mica flakes can physically rotate, aligning themselves perpendicular to the maximum stress.
Get pushed into alignment.
Right. Or during recrystallization, new platy or elongated minerals might grow in that same aligned direction from the start.
So new minerals grow lined up.
And even spherical grains can flatten through solid-state flow, where the crystal structures slide relative to one another, or by pressure solution, where ions dissolve from areas of high stress and deposit in areas of lower stress, changing the grain's shape.
So grains themselves get squished or reshaped. Interesting.
These processes create different types of foliated textures. At the lowest grade, you might see slaty cleavage or rock cleavage.
Like in slate tiles.
Exactly, which allows rocks to split into thin, flat slabs, almost like pages in a book. Slate is a prime example, forming from low-grade metamorphism of shale, mudstone, or siltstone.
That makes sense why it's used for roofing.
Its excellent cleavage makes it super useful, yeah. And its cleavage often forms at an angle to the original sedimentary bedding, which is a key clue.
Then, at higher grades of metamorphism, you get schistosity. What does that look like?
Imagine those tiny, almost invisible mica flakes in slate. Now, under even more intense heat and pressure, they've grown into larger, sparkling crystals of muscovite and biotite.
Bigger, visible flakes.
Yes, and they're still aligned, creating a very distinct, often wavy, planar layering, giving the rock a sort of scaly or shimmering appearance. Rocks with this texture are called schist, like a mica schist or a garnet mica schist.
Just, okay, sparkly and layered.
These often also contain flattened quartz and feldspar crystals, embedded among the mica grains. And at the highest grades, we observe gneissic texture or gneissic banding.
Gneissic banding sounds like stripes.
It is. During high-grade metamorphism, ion migration actually leads to the segregation of light-colored minerals like quartz and feldspar from darker ones like biotite and amphibole. This creates a very distinctive, often wavy, banded appearance. Rocks displaying this are called gneiss.
Nice, Gneiss.
That's the one. And they frequently show clear evidence of intense deformation, like intricate folds within those bands.
But not all metamorphic rocks are foliated, right? Some just bake without being squeezed in a particular direction.
Precisely. Some have non-foliated textures, meaning they don't show a preferred mineral alignment. These typically form where the deformation is minimal, and the parent rocks have crystals that are roughly equidimensional, like little cubes or spheres.
Like calcite or quartz grains.
Exactly. So there's no preferred direction for them to align.
Classic examples of these non-foliated rocks include marble, which forms from the metamorphism of limestone or dolostone.
Ah, yes, beautiful stuff.
Pure marble is a beautiful white, composed of interlocking calcite crystals that can be quite large. It's prized for sculptures and monuments like the Lincoln Memorial or the Taj Mahal.
Though its calcium carbonate composition makes it susceptible to acid rain, unfortunately.
Right, a vulnerability. Impurities in the parent rock can also give marble various colors, pink, gray, or green.
Another great example is quartzite, which is formed from quartz sandstone. The quartz grains fuse together, making it an incredibly hard rock.
Harder than the original sandstone?
Oh, much harder. It often breaks across the original grains, not around them. Pure quartzite is white, but iron oxide or other dark minerals can add color.
And then there's hornfels. What's that one?
Hornfels is a fine-grained, tough, dark, non-foliated rock that typically forms when shale or other clay-rich rocks are baked by a hot magma intrusion, kind of like pottery fired in a kiln.
Baked shale becomes hornfels. Got it. And occasionally you'll find unusually large, distinct crystals within a finer-grained matrix in metamorphic rocks. What are those called again?
We call these porphyroblasts. Think of them like the unexpected chocolate chips in a cookie, larger, more prominent crystals that manage to grow significantly during the recrystallization process.
Like garnets in a schist.
Garnets are a classic example of porphyroblasts, yes. It's a sign that conditions were just right for those particular minerals to really take off and grow large, while the rest stayed finer.
Okay, so we have the agents, the textures. Now, where does all this happen? If we connect this to the bigger picture, different tectonic settings create unique conditions for metamorphism, right? Each leaving a distinct signature in the rocks.
Exactly. It's not just a random process, but a direct consequence of Earth's internal engine and plate tectonics. Different environments produce different results.
So we're talking about different workshops where Earth's geological sculptors are at work, each with their own specialized tools of heat, pressure, and stress. First up, we have contact or thermal metamorphism. What's happening there?
This type occurs in Earth's upper crust, meaning relatively low pressure, when rocks are baked by a molten igneous body.
The magma intrusion again?
Right, so high temperature is the key factor. The result is a zone of alteration around the intrusion called an aureole, like a halo of changed rock.
An oil. Okay.
Because directional stress is minimal here, the resulting metamorphic rocks like hornfels from shale, marble from limestone, or quartzite from sandstone are typically non-foliated, just baked, not squeezed.
Next, hydrothermal metamorphism. This sounds like it involves water, and that water must be doing some serious work.
It does. This is where hot, ion-rich water circulates through rocks, causing chemical alteration. It happens at low pressure and low to moderate temperatures.
So fluids are the main driver here.
Yes, these fluids enhance recrystallization and facilitate ion movement, sometimes even changing the rock's overall chemical composition, that metasomatism we talked about.
Metasomatism can happen here too.
Definitely.
Yeah.
This process is incredibly important because it creates economically valuable deposits of copper, silver, and gold. It's most widespread along mid-ocean ridges where seawater reacts with hot oceanic crust.
Under the ocean.
Yeah, forming rocks like serpentinite and soapstone and creating those famous black smokers that precipitate metal sulfides, like the copper ores once mined on Cyprus.
Wow, so it's linked to valuable resources. Then there's burial metamorphism. This sounds pretty straightforward, just bury a rock and it changes.
Essentially, yes, though it needs deep burial. This occurs where massive amounts of sedimentary or volcanic material accumulate in subsiding basins, such as the Gulf of Mexico.
Like thick layers piling up.
Exactly. The sheer weight of overlying material creates confining pressure, and combined with the geothermal gradient providing heat, drives a low-grade metamorphism. Nothing too dramatic, usually.
And closely related is subduction zone metamorphism. This happens along convergent plate boundaries where cold, dense oceanic crust descends rapidly into the mantle.
Right. Here, pressure increases much faster than temperature because the slab is cold and sinks quickly. And differential stress plays a major role in deforming the rock as it's metamorphosed. High pressure, lower temperature.
A very specific PT path.
A very specific path, yes. Now, our most widespread type, and perhaps the most dramatic in terms of scale, is regional metamorphism.
Regional. Covering large areas.
Vast areas, yes. This is typically associated with mountain building from continental collisions, like those that formed the Appalachians or the Alps. You have intense deformation, high temperatures, high pressures, and significant differential stress, all acting together.
The whole package.
Pretty much. The result is truly massive belts of folded and faulted metamorphic rocks, often intertwined with igneous intrusions, forming the very cores of mountain ranges.
So the hearts of mountains are often made of these rocks.
Very often, yes. This process produces that classic sequence of metamorphic rocks you might recognize: slate, phyllite, schist, gneiss, quartzite, and marble.
We also have some more localized types, right? Like along faults.
Good point. Metamorphism along fault zones. Near Earth's surface, rock behaves in a brittle way, so movement along a fault can pulverize rock into what we call fault breccia, just crushed rock.
Okay, near the surface, but deeper.
At great depth, where rocks flow ductily under pressure and heat, the mineral grains can elongate and smear out, forming finely laminated rocks called mylonites.
Mylonites. So faults create different textures depending on depth.
Exactly. And finally, there's impact, or shock, metamorphism. This is incredibly dramatic, happening when high-speed meteoroids strike Earth's surface.
From space?
Yes. The intense heat and shock waves pulverize, shatter, and even melt rock, forming what are called impactiles, and sometimes creating rare, high-pressure minerals like coesite or even diamonds.
So a space rock can literally make diamonds on impact. That's wild.
It is. These are processes of extreme instantaneous energy transfer. Very unique conditions.
So if we find a metamorphic rock, say out in the field, can we tell how intense the baking and squeezing were that it experienced deep inside the earth? Can we truly read its history?
Absolutely. That's a huge part of geology. This raises an important question. How do geologists reconstruct these past conditions? We look for systematic variations in texture and mineralogy across different metamorphic zones.
Metamorphic zones, okay.
As the intensity of regional metamorphism increases, you'll generally see a coarsening of the grain size. The crystals get bigger with higher grade.
That makes perfect sense. So starting from a sedimentary rock like shale, as the metamorphic grade increases, it might transform into a fine-grained slate, then to a phyllite with a glossy sheen, then to a medium-grained schist with a scaly foliation, and finally to a coarse-grained, distinctly banded gneiss.
That's the classic progression. Our sources mention you can observe this by moving west to east across the Appalachians.
Right, I remember reading that.
From flat-lying shales in Ohio to folded slates in Pennsylvania, and then to the schists and gneisses found in places like Vermont and New Hampshire. It's like a geological road trip through increasing metamorphic grade.
A real-world example laid out.
In addition to textural changes, we also look for index minerals. These are specific minerals that are precise indicators of the metamorphic environment, particularly the temperatures and pressures in which they formed.
Earth's thermometers and pressure gauges.
Exactly. Geologists can map the presence of these minerals to distinguish zones of varying metamorphic grades. For example, chlorite typically forms at low-grade conditions, less than about 200 degrees CD.
Chlorite means low grade.
Generally, intermediate-grade metamorphism might be indicated by minerals like garnet or staurolite,
Garnet and staurolite for medium grade.
and at the high-grade end, where temperatures exceed 600 degrees C, you might find sillimanite.
Sillimanite. And what's fascinating is that sillimanite is so incredibly durable and heat resistant that it's even used to make specialized porcelains for extreme environments, like spark plugs.
That's right. So these tiny crystals are not just geological clues, they have real-world applications today because of those properties formed under extreme conditions.
Amazing. Now, what happens at the most extreme end? Can things get even hotter?
They can. In the most extreme environments, even the highest-grade gneissic rocks can begin to partially melt. This process results in what we call migmatites,
Pegmatites, mixed rocks.
literally mixed rocks. What's interesting is that light-colored silicates, like quartz and potassium feldspar, have lower melting temperatures and melt first, while the darker metamorphic silicates like biotite and amphibole remain solid.
So part melts, part stays solid.
Exactly. When this mixture cools, you get a rock with light, igneous-appearing bands swirled together with dark, unmelted metamorphic bands.
Wow, a true hybrid.
They beautifully illustrate the transition zone between metamorphic and igneous rocks and can be difficult to classify into just one category. They're literally a blend of melt and solid rock.
This is where we really put all the pieces together, right? Using these textures and minerals, like using a plant community to figure out a climate zone, we can use specific groups of minerals to define geologic conditions. It's like Earth has its own diagnostic language.
Exactly. The Finnish geologist Pentti Eskola developed the concept of metamorphic facies back in the early 20th century.
Metamorphic facies.
Simply put, rocks containing the same assemblage or group of minerals belong to the same metamorphic facies, implying they formed under very similar temperature and pressure conditions. This concept is incredibly useful in interpreting Earth's history for the rock record.
So finding a certain group of minerals tells you the P&T conditions.
Precisely. And there are several common metamorphic facies, with names like hornfels, zeolite, green schist, amphibolite, granulite, blue schist, and eclogite facies.
Those names sound specific.
Their names are often based on the minerals that define them, for example. The green minerals, chlorite, epidote, and actinolite in the green schist facies, or hornblende in the amphibolite facies. They denote specific temperature and pressure conditions, helping us understand the tectonic setting where they formed.
And these facies connect directly to plate tectonics, don't they?
Absolutely. What's fascinating is how these metamorphic facies directly connect to specific tectonic environments. For instance, in subduction zones, where cold, dense oceanic lithosphere descends rapidly, pressure increases much faster than temperature.
High P, low T.
Right. This high-pressure, relatively low-temperature environment is characterized by the blue schist facies, named for the distinctive blue glaucophane amphibole found in these rocks, like those in California's Coast Range.
Blue schist means subduction.
Often, yes. Deeper subduction can lead to the even higher pressure eclogite facies, indicating very high temperatures and pressures deep within the subducting slab.
Okay, and what about regional metamorphism, like mountain building?
In regional metamorphism settings, like continental collisions, you typically see increasing temperature and pressure together. This leads to a characteristic sequence of facies, often starting with zeolite, then progressing through green schist, amphibolite, and finally into the very high temperature granulite facies.
So a different sequence for a different tectonic setting.
Exactly. And contact metamorphism, being high temperature but low pressure, typically produces the hornfels facies.
It's also important to consider mineral stability and polymorphs, right? Some minerals are stable almost anywhere, but others are pickier.
Very true. Some minerals, like quartz, are stable over a wide range of conditions, but others, like the polymorphs kyanite and dellicite and sillimanite, all sharing the same chemical composition of altoase IO5, but with different crystalline structures, are very specific indicators.
Alto-SiO5, but three different minerals depending on P and T.
Precisely. These are like Earth's precision thermometers and barometers. And lucite suggests high temperature and low pressure, often from contact metamorphism.
Andalusite, hot, not deep.
Kyanite points to high pressure and lower moderate temperatures, common in subduction zones or deep burial during mountain building.
Kyanite, deep, maybe not super hot yet.
And sillimanite forms only at very high temperatures, whether from contact with hot magma or extremely deep burial, often associated with high-grade regional metamorphism or granulite facies.
Sillimanite, very hot, deep, or near magma.
The relevance here is profound. Imagine finding kyanite in a rock in, say, Scotland. That single mineral tells geologists that millions of years ago, that part of Scotland was under incredible pressure,
Wow.
likely from a mountain-building collision or even a subduction event, painting a picture of a vastly different tectonic past. It's truly like decoding Earth's autobiography.
Reading the rock story.
Reading the specific conditions of temperature and pressure that a rock experienced millions of years ago, all from a tiny crystal or an assemblage of crystals.
Wow, what an incredible journey into Earth's most transformative processes. From shale becoming slate, to the formation of majestic marble statues, to the precious metals we mine. Metamorphism truly is Earth's hidden sculptor. It's happening constantly, shaping our planet in ways we can barely imagine.
hmm This deep dive really shows us that these rocks, often seen as inert, are actually dynamic archives. They record the intense heat, crushing pressures, and powerful stresses of Earth's internal engine,
Yeah.
providing an essential window into our planet's history and ongoing geological activity. It's all recorded there if you know how to read it.
Absolutely. So the next time you see a piece of gneiss or a marble countertop or even just a mountain range, consider the untold stories of transformation embedded within. What other silent witnesses of Earth's past are just waiting to be read right beneath our feet?
Makes you think, doesn't it?
It really does. This has been The Deep Dive. Thank you for joining us on this exploration of metamorphism and metamorphic rocks. Keep digging into the wonders of our world.